So I will mainly talk about the application of Cerenkov for endoscope use. But before I talk about that, I want to also talk about some background about Cerenkov Luminescence Imaging. As we all know, multimodality medical imaging is a trend for our society, and people try to combine different modalities together, such as PET, CT, PET, MRI. So that's some conventional way to assemble different modalities together. But recently there are new trends. So those trends actually is, to me, is more like a hybrid medical imaging. So they take advantage of like one modality, use one component from a certain modality and then another component from another modality, and then put them together and come out with a new modality. So like Cerenkov Luminescence is perfect example for that kind of approach. So basically you use radionuclide. You need to use radionuclide from usually that's used for nuclear imaging, and then you also use optical imaging instrument to capture the signal and to obtain an imaging. So basically, you bridge the nuclear imaging and the optical imaging, and come out with this new kind of imaging technology, named as Cerenkov Luminescence Imaging. Another one is photoacoustic imaging. So basically for photoacoustic imaging, you need to use a laser, fluorophore, and those are generally like for the, those are commonly used for fluorescent imaging, optical imaging modality. And then you use the ultrasound to monitor the signal. So you also use some component from ultrasound imaging, and then you come out with this photoacoustic imaging. So it's quite new, it's different from fluorescence, from ultrasound, but it's come out from those two modalities. So those hybrid imaging modality is a new way to design. To me, I like to invent a new imaging modality. So as Dr. Gorima already introduced about the physics of Cerenkov imaging, what's that about, what's the basic concept. So the key concept is really you need the particle. It's a charged particle which have very high speed, even higher than the light of speed in that particular medium. So basically you need to take advantage of this equation, the Einstein energy and speed equation, and you put the if you say like for a certain radionuclide, they emit a particle with different energy, and then you put that energy in, and then you calculate the speed. Usually they have a very high speed, and then like for the you also need to consider about the refraction index of the speed in certain medium, like in the water. So the light in that the light in the water is not C. 1C is actually lower than 1C. It's around 0.75 C. And then if you use the 0.635 MeV positron, the speed is 0.89 C. So it's higher than the regular the light in that medium. So that's why it can generate Cherenkov photon. And also, if you consider about the other, say if you put this 7.5 C, and then you calculate the energy, any radionuclide with the energy higher than 0.268 MeV can generate a Cherenkov photon. So 0.268 is not so high. So that's why for many positron, many charged particles, they can produce Cherenkov photon. So here is what we shown before. Different radionuclides can produce Cherenkov photon and then be used for imaging. So this is just a regular luminescence imaging. But for the gamma particle technetium 1990M, you don't see any signal from this kind of radionuclide. And for the application, once this Cerenkov luminescence imaging this term was given, and then people try to find a different application for this technology. To me, we can talk about many different applications, but today I will just briefly mention about a few and then talk about the endoscope. So you can use Cerenkov luminescence imaging to measure the radiochemical purity. So before, when you try to measure the radiochemical purity, you usually need to run the TRC and then put it into the TRC scanner and then you cut the TRC piece by piece and then count the radioactivity of each piece and do the calculation. But now with this kind of Cerenkov luminescence technology, you just simply put the TRC plate into the optical image, and then you can do the calculation, and that's very convenient and was demonstrated by this Korean group before. In their paper, they also demonstrated Cerenkov luminescence can be used for plant imaging. So you dip the plant into like a P32 labeled phosphoric acid, and then develop the leaf and then put it into the optical imager, and then you see this kind of distribution of the radio tracer. So this gives very interesting information. Potentially they can be used to study like plant biology. And especially Dr. Garima talked about all different kind of application for using Cerenkov for small animal imaging. Basically, you need to consider about the emission spectrum of Cerenkov luminescence, as well as the biological tissue, their autofluorescence, their absorbance. So this near-infrared window, the Cerenkov luminescence, really for different radionuclides, their spectrum have very good overlay with this biological tissue emission window. So in this near-infrared range, we can see very good signal from all different radionuclides, so potentially they can be used for in-favor imaging. I just want to point out one unique feature of Cerenkov luminescence spectrum. They are continued wavelengths, so you really can take advantage of this continued wavelengths. So you can select whatever you want, different range of wavelengths for in-favor imaging. You can either do like 5 to 600 or 7 to 800, and you can do multiple wavelengths imaging, or you can use open wavelengths, like range from very low to very high. You use very broad wavelengths for in-favor imaging. So different selection, different wavelengths potentially can give you some better idea, like a different signal to background contrast. Compared to conventional fluorophore, so like Psi 5.5 or X680 or some nanoparticle, those fluorophore usually they can only produce very sharp peaks. They are not produce continuous emission wavelengths. So you really cannot do this kind of imaging them using different window. And here just shows several examples of using Cerenkov luminescence for in-favor imaging. This is the first one people shown using F18 FDG for tumor imaging, and then shortly we demonstrated the same concept using this one for C6 tumor imaging. Here shows Dr. Garima shows using the zirconium 89 for in-favor imaging. So as you can see here, really the FDG accumulated in the tumor very well. You obtain very similar information as micropet. And also you can use Cerenkov imaging to study a reporter gene reporter probe system. Like here, this is the conventional reporter gene reporter probe system, the HSVI-t, and then you use the FHBG or gansequivir, some radioformulated gansequivir for in-favor imaging. For this FHBG system, like here the C6TK, and then you use FHBG to incubate with the transfected cells, and then they show very high uptake. But for non-transfected cells, they don't have a high uptake of your probe, and then they don't show any signal in this optical imaging modality, the Cerenkov Luminescence Imaging. So you can immediately know the transfection works very well, and you have stable, you have the cells which can express the TK gene. And this is the in favor data. So on the one side is C6 transfected with TK, on the other side is just the wild type C6. They don't show, they do show very high uptake in the transfected cells, while don't show any signal in the wild type. So this is the Cerenkov Luminescence Imaging at 1 hour, 2 hour, but this is the micro-PET data, PET images at 1 hour, 2 hour. So basically they provide similar information from these two imaging modalities. You can really take this advantage and use the Cerenkov Luminescence as a substitute for PET imaging. People also demonstrate you can do this for the radio iodine. So this is F18 imaging, and then if you can do the iodine supported imaging, so really you can use this CLI for report gene, report probe monitoring. And to me, I think for the preclinical research, Cerenkov Luminescence imaging is especially important for the drug development, for monitoring tumor treatment. So here we just show one example. We just want to verify whether Cerenkov Luminescence can give similar information as PET imaging when we use that for drug therapy monitoring. So here we use the we use two different tumor models. One is H460, another is PC3, and then we use afacitin to treat the tumor. After different days, we give the mice with F18-DG or F18-FLT for monitoring treatment efficacy. Here just shows the data. Basically, and this data looks quite complex, but the key information is when you see change using the micro-PET, you see the same change from the Cerenkov Luminescence imaging, like in these pictures. Here, when we treat the tumor model with afacitin, the tumor size were reduced, and then the FLT uptake were reduced also. So as you can see here, the uptake reduced, and then the micro-PET also show reduced uptake. And for other controlled, the uptake, they're low change, and then for both Cerenkov Luminescence and micro-PET, they're low change. And we can do the correlation assay to verify these two modalities have very high correlation. So especially for the subcutaneous model, tumor model, you can really use Cerenkov Luminescence imaging to evaluate the drug treatment. I think this is just very good for the drug development industry. So another important application for people are trying to work on is develop Cerenkov Luminescence tomography. So all those CLI imaging I mentioned before is just obtained from conventional IFS system. That's the 2D information. Like for this one, people are using the people in the UC Davis and one group from Chinese Academy of Science. They're trying to develop Cerenkov Luminescence tomography, and they show they can image deep tissue like heart and provide very good contrast and high resolution. And in another example, this is also from Chinese Academy of Science. They try to combine Cerenkov Luminescence tomography with SPECT. So basically, their idea is using the SPECT to image the deep tissue, and then the information from the SPECT can guide them to better reconstruct Cerenkov Luminescence images. So this can provide, they use some algorithm to generate a better imaging. So as Dr. Kramer also talked about, when we think about Cerenkov photon, right? What's their other application. So definitely they are a light source, so they can be used as a new way to excite fluorophore. So like here, conventionally we always use the gamma ray, the positron. They produce two photons, and then that can be used like a PET imaging. And then with this Cherenkov photon, because they are continuous wavelengths and they're broad, they can excite multiple fluorophores simultaneously. Like we shown here, we use 3 different quantum dots, like QD 655, 705, or 800, and then we can use the same radionuclide, like iodine 131, to excite multiple fluorophores simultaneously. And if you're interested in this work, you can check the reference. And here people shows the similar concept, like using different radionuclides, different quantum dots, different fluorophore for in favor imaging. Like in this work from the Washington St. Louis group, they use the quantum dot and then copper 64 for excitation. And this one is from Korean group. They also use iodine 124 to excite quantum dots. And this one, people demonstrate they can really use radium, the beta particle, to radium 188 to excite up conversion nanoparticle for in vitro imaging. So just the same concept. And here, people also shows like they can use F18 or actinium-74 to excite European nanoparticles, and they show the emission peak, and then this is just an in vitro study. I think another interesting application is for instead of for excitation of the fluorophore, you can also use the Cherenkov luminescent light as a source to cleave chemical bond. I think this is a really interesting concept. Like shown in this study, the group from Harvard, and they use basically they use a small molecule to a cage to cap the luciferin. And then this chemical bond is light sensitive, and then they can use the Cherenkov light to cleave this chemical bond and then release the luciferin. And then this luciferin can be a substrate for in vivo bioluminescence imaging. Here just shows the concept, and then here you can see all the in vivo validation of their concept. They use FDG to excite the to cleave the this bond. So these are all different application of using Cherenkov photon for in vivo application or for small animal imaging. But all those research, mainly you need to use small animal imaging modality. So how can we move this forward? Whether the Cherenkov luminescence imaging technology have any role in clinical imaging? That's the question we're keep asking us. So to me, I think most possible potential application, really we need to build a Cherenkov luminescence endoscope technique, as Dr. Grimm already demonstrated before. They use this small animal imaging system to demonstrate you can do the Cherenkov luminescence endoscope. So for us, we want to move forward. So we try to build such a Cherenkov luminescence endoscope system and then use it for imaging. For like for small animal imaging, when you use this small animal optical image system, you put the animal in a dark box, so you already block all the ambient light. That's not a problem at all. But for clinical imaging, you really don't have this luxury to do this. So you need to use the endoscope and put it inside of the whole human body. And then those, the hollow organ or the insufflated cavities, such as the colon or the bladder, right? Those can serve as a natural box, dark box, to block the light from outside, and then you can potentially use this endoscope technique to identify the small lesion. Here we just developed the first prototype CLE Cerenkov Luminescence Endoscopy system. You can also find abstract and poster presentation for this work. If you are interested, you can talk to the first author of this work, Raj. The abstract is P378, so he's here, so you can meet with him and discuss this work in more detail. So basically, we just still use the conventional small animal imaging system because they have a CCD camera, and then we put some optical fiber and inside of this CCD camera, and here we put our studying subject like the phantom or small animal outside, and then we can do the imaging. So here we just used a couple of different endoscope or fiber we can find and then use and test them. So basically here we just showed a couple of different fibers. Like this one, the first one we used the flexible cystoscope, and then another one is the rigid cystoscope, and then we also used the 6 mm fiber optical bonder, and then this one we used the 400 micrometer or 60 micrometer fiber optical cable. So this is several different optical fibers we can find, and then we test them. And here just shows some parameter of different fibers. And here shows their detection sensitivities. As you can see from this slide, we found in general, the 6 mm fiber optical band, they shows much higher signal comparing to the other fiber we tested. So this one looks like it has a higher sensitivity. Here shows like those fibers for testing different quantity or different amount of radioactivity. So we put the active phantom with the system and then let them decay. So then you do the calculation. You also measure the singular, and then you can obtain this kind of curve. It shows for this 6 mm fiber, it has the highest singular compared to all other 5 fibers we tested. So we then use, looks like this one is the most promising one, then we move forward and also use this 6 mm system, fiber system to obtain the Cerenkov luminescence spectrum. So it shows very similar spectrum as we obtained from conventional IFIS system. Here we also did some brief calculation. So if you see this is the detection sensitivity. Looks like this 6 mm fiber can only detect 1 microcurie level of radioactivity. So 1 microcurie, that's not so exciting, but that's also okay. So it's not too bad. So we did this calculation. In the reference, it reported the SUV for FDG in the bladder cancer is around 4.5. So if you inject a 10 millicurie F18 FDG and there around 1 microcurie probe is expected in bladder cancer at 2 hours post-injection. So 1 microcurie actually is a clinically relevant activity. So if our system can detect 1 microcurie, so potentially they can be used for detection such lesion, right, like bladder cancer. But still, we think we still need to push our detection sensitivity up to like 0.1 microcurie or even lower. So how to improve that? There are a couple of parameters we can optimize. So those like include using different diameter of optical bond, and they have different parameters. You can also use different radionuclides. F18 is not the radionuclide with highest Cherenkov photon production, so you can use other radionuclides such as yttrium-90, although I think yttrium-90 is mainly used for therapy, but like rhenium or some other radionuclides potentially have higher photon production yield can be used, and also you can explore higher sensitivity CCD camera. Here we also test our system for in-favor imaging. So basically, we inject F18 FDG to this mice bearing C6 tumor, and then we put our bundle, right, the fiber at different location of the mice. And here, if you see the brain, it shows quite high singular. And then if you see other normal like a muscle, right, here it's relatively low. And then if you see the tumor, it has a much higher uptake. And then we can also take out all the organ and use the same fiber-based system, the CLE system, to measure their uptake. And you can see like this, it shows very good signal from a tumor, from the heart, but much lower from the muscle. You can also do the quantification analysis to verify the good uptake from the tumor. This is the one system we tested right now. Meanwhile, we also developed another system. It's just a different fiber. So this one, the fiber is a little longer, and then they have multiple small fiber with like 10 micrometer fibers, and then it's packed inside of this laparoscopic system, and then we just put this one with inside of this IFIS system. Then we can use the CCD camera to monitor the singular. And then here we also measure the sensitivity of this custom-made fiber optical system. We found this one also only shows only can detect 1 microcurie activity. So if we, as you can see here, if you want to see the low activity, the noise is too high. So 1 microcurie looks like it's the one we can achieve right now. We also test the resolution for this system. As you can see here, this is the phantom, and then this is the one obtained from the IFIS 200 system. And then this is the one we use the CLE system, the in-house CLE system. So this the phantom with 1.2 millimeter, and here is 1.6 millimeter. So really you can see the 1.6 millimeter phantom can be well separated. So the detection resolution is okay. And then we further demonstrated the use of this CLE system for imaging guided surgery. So basically we use the tumor mice, and then we remove the large portion of the mice, and then we intentionally keep a small tumor residue, as shown here. And then we put this, we inject F18 FDG, right? And then we put inside of the conventional IFIS system. And then you can see the tumor residue will light up. And then after we see this singular, we remove the tumor tissue completely, and then put the mice back to the IFIS system again. You can see here, you don't see any singular from this region. Here, this is the tumor. And then we simultaneously use the CLE system to monitor this procedure. As you can see here, this is the tumor residue. Looks like it's composed by the 2 pieces of tumor residue. And then you can remove that. And here, it shows very low activity in the in this region. So looks like this CLE really provide a quite high resolution and can help us to identify the small lesion of the tumor. I want to give some brief summary of our work. As Dr. Grimm already summarized the advantage of the CLI, Cerenkov Luminescence Imaging, I think the CLE system has a similar advantage and disadvantage as the CLE, right? CLI. The biggest advantage for Cerenkov Luminescence Imaging is there are lots of probe available, like many already labeled compound have been tried in our community, and many of them were already approved by FDA, so they can be quickly tested in clinic. And CLI or CLE system is also very easy to use. They're very cheap and have very high resolution. And especially for this kind of imaging modality is inherited multimodality imaging method. You can do the nuclear imaging, you can do the optical imaging. If you label nanoparticle or label fluorophore, you can also do the optical imaging, or you can do several imaging modality together. But the disadvantage is still they are radioactive, and especially for CLE system, right now looks like we have the sensitivity is not as high as we wanted. We really want to push the detection sensitivity to like 0.1 or 0.01 microcurie level instead for 1 microcurie we can achieve currently. And lastly, I think we demonstrate the concept of using the Cerenkov luminescence imaging for endoscope application. Although 1 microcurie is not so great, but there's still clinical relevant. We still believe the CLE is a promising modality for future clinical application. Finally, I would like to acknowledge several people in my lab, especially Simon Liu and Brian Xu. Simon is the main worker for this project, and Brian demonstrated the application of a CLI system for drug evaluation. And then my collaborator, Dr. Gambier and Raj, and Dr. Neishin and Colin, we work together to develop this Cerenkov endoscope system, and the funding from NIH. Thank you.